question. This connection between calculating, use this analytic formula mechanically versus this, what's happening to this patch-to-patch, directional derivative and velocity of this vector thing. Does it make more sense than last time? Okay. So at this level, all the way down here, there's no clocking backward. But if the denominator is a complex number, if you actually divided that, and there's one more thing that gives you actually always the same answer. Ignore all the other answers. That seems like weird, but if you combine these two things, amazing statement comes out. What is that called again? Cauchy-Riemann equation. Right? But before I enter and introduce this Cauchy-Riemann equation, I'm going to do one more thing about this map. All right, I came back in here. There's no complex numbers. These u and v is obtained from complex functions, but I'm just looking at x and y and u and v, and there's no complex numbers. Is that okay? All right. So if I'm looking at that problem there, I'm going to draw a line like that. I'm continuing from that. It's exactly the same function. U is there and v is there. Okay? Now here's the domain. X and y. I'm looking at 1 plus 1 comma 1, which is there. And here's a uv. Does anybody know where that one goes? 1 comma 1. 1 plus I. 1 comma 1. Here's a u and v. You plug in 1 comma 1 there to get that value, right? Where does that go? 0, 1, 1 is a 0 comma 2, right? So here's a 0 comma 2 over there. So that's a 0 comma 2. That's point P, that's point Q. Make sense? It's actually happening in the level of complex, but we're just looking at the two real number going to two real numbers. Good? All right. So if I'm moving toward that direction, like that velocity vector, doesn't that velocity vector look like E1 plus E2? Does this notation make sense? E1 is your horizontal vector, 1 unit. E2 is vertical vector, 1 unit. Right? So that's a position, and that's a velocity vector. This point is moving toward that direction. E1 plus E2. This is called point of application, and that is a velocity vector. What is the speed of this velocity vector? How fast is this one moving? That's right, modulus of this vector. What is it? Right, first one's 1 plus E2. How do you calculate the vector, length of a vector, E1 plus E2? One, 1, so 2, right? But the square root of 2, remember? That's the hypotenuse of this vector, right? The square root of 2. So is it moving to the direction of 45 angle and how fast? Square root 2 units. That's what this E1 plus E2 represent as a velocity vector. So if I'm moving to that direction like that, how fast is this one image is moving? That's the question I was addressing all in this discussion. Is that right? That's what I was thinking. So let's calculate that. What was the magic? And this is the velocity vector v. What do we multiply? What is that matrix called? Jacobian matrix, right? What was that? Ux, Vx, Uy, and Vy. I think we already calculated Ux. What's Ux? Do you know where the Ux? U is this and V is this, right? So what is Ux? 2x. What is Uy? Negative 2y, right? What is Vx? 2y. What is Vy? Is that 2x? Is this right? Okay. This is applied at what point? This velocity vector is happening in what point of application? X equals y equals what point? 1 comma 1, like the Jonathan said. This is the point of application. That's what's happening. If you have that x and y value, all the other velocity phenomenon is governed by this matrix with x and y value what? They usually write it this standard notation. X and y being what? 1 and 1. That's the starting point of application. Now, what is this matrix? X equals 1 is a 2, right? Y equals 1 is a negative 2. And here's 1 is a 2. And here's a 2. That's the vector. That's the matrix. Oh, what are you multiplying in here? What's V? What's the coordinate of V? If I write E1 plus E2, what's the coordinate in terms of E1 and E2? E1 will be coordinate 1, 0, right? E2 will be coordinate 0, 1, remember? So what is E1 plus E2? Coordinate 1, 1. So that coordinate 1, 1 is multiplied in there. So let's do that. What is it? You get the 0, right? And then a 4. So where is the 0 and 4? That's what kind of vector is that? It's a velocity vector, right? If you're moving root 2 speed to 45 degree, and where is this one moving? Which direction? 90 degree, right? 0, 4 is 90 degree up there. And what is the speed of this vector? 4, 0, 4. Because of the 0, you square it, and that's exactly the length of this vector. It's a 4. All right? That's what this means. If you move it in a certain direction with a certain velocity vector, what happens to the image? That is completely determined by this Jacobian matrix. If you choose a different point, different Jacobian matrix, completely given by your point of application in the domain. Okay? So that's what's happening right here, actually, under that. So that's one vector, E1. This ux, vx came from here is a 2x, 2y. E2 is going where? Negative 2y, positive 2x, right? Good. So that's where they go. Can somebody come up with a nice relationship between these two vectors? Some of the things that you do in a Calc 3 when two vectors are introduced. Some relationship between the vectors, right? Like angles, like the length of this vector and things like that. This is a very important part. If you understand this thing, that everything, the rest of the semester will be, you have a very, very good picture of what's going on in the complex functions. So here's an first we're about to witness this thing. So how about angle? Can somebody come up with an angle? To come up with an angle, what do you do? If I give you two vectors, how do you calculate the angles? What kind of thing do you do? Something called some product, right? The dot product? If you dot product, it'll tell you the cosine theta value, right? So what happened if you dotted? E dot E2? Can somebody do that? X coordinates multiplied, what is it? Negative 4xy, is that right? And y coordinates multiplied, right? Well, it's a positive 4xy, sorry about that. Y coordinates multiply, I was right. X coordinates become negative, y coordinate become positive, right? What is it? 0. What do you know when the dot product is 0? 90 degrees. So there are 90 degrees. What is 90 degree? I was wrong. This is not E1 and E2. Sorry about that. E1 and E2. It should be W1 and W2. That's the image, right? E1 is 1, 0, and 0, 1. Sorry about that. So I'm going to change that to W1 and W2. And I'm going to name that in here W1 and W2. E1 went to a certain direction, E2 went to, we just verify they're 90 degrees. How about E1 and E2 relation? Are they 90 degree? They're 90 degrees, right? So the angle 90 degrees preserved just for that two vectors. Okay? How about the magnitude? What is the magnitude of W1? Here is a formula of W1. Can somebody calculate that? Root, right? (4x squared plus 4y squared). Is that right? This is x coordinate and y coordinate. That's the length of the vector. Correct? How about W2? In different order, it's the same thing, right? So E1 and E2 is kind of rotated, exactly not keeping the 90 degree, and how much is each of them are stretched apart? Exactly by the same factor, right? So E1 has length 1, but W1 has length whatever that is. E2 has length 1, which is this one, and its image, W2, also has exactly the same length, right? So isn't the velocity map is supposed to be, the linear map is completely given by this matrix called the Jacobian matrix, right? So what it did is that it rotated E1 and E2, keeping the angle between E1 and E2 exactly the same, and by stretched a little bit by exactly the same factor. E1 is stretched by same factor, E2 is stretched by same factor. So this Jacobian map is rotation followed by dilation. Rotation is a linear operator. If you take velocity vectors, all sorts of velocity vector, you rotated everything, then it's a linear. And dilating is a scalar multiplying everything by the same factor. That's a dilating. So we just discovered that what is happening in the entirety of velocity vector, how the velocity vectors move to this velocity vector is just simply rotation by the same angle and dilation by a little bit. Okay? So because of that, it preserves all the other angles. If I have dilation, because of that fact, if I have two arbitrary vector v1 and v2, not necessarily same length, then what happens is that if you have the angle theta, and they're rotated w1, w2, stretched by exactly the same factor, because it's rotation, that angle is exactly the same. And it has this important property. Any polynomial map, nice maps with elementary function we look at in here, or this of the fact that this one exists imposes a condition that what is happening to locally to velocity vector is just simply rotation and a little bit of dilation. If you go to a slightly different point, amount of rotation, amount of dilation changes, but a fixed point, if you look at all the velocity vector, what happens is it just rotate a little bit and dilation. Okay? This map is completely obtained by multiplying single complex number. Multiplying single complex numbers, alpha, it involves e to the x and e to the yi, right? E to the x will be the dilation, e to the yi will be rotating a little bit by de Moivre's theorem. So as if it is a locally, it is obtained by multiplying one complex number, and which is the first coefficient of a Taylor series of this map. So that's going to be recovered through this machinery. All right, so my point here is that there's the two sides of this picture. One side is this mechanical calculation, and its geometric meaning is actually far more complicated and difficult and requires a lot of Calc 3 knowledge to understand what's happening, but you end up at this matrix. And that matrix, together with that, everything has to be that one. As you clocking backward, it'll impose interesting condition. All right. So here, it's one last thing. So E1 goes to where? Anybody remember? Under what vector does that go to? It's a little review, but at the end there's bang. There's this nice statement. E1 goes to where? This is u comma v, and it's differentiated, right? E1 is this x direction, only x is moving. Therefore, ux and vx. All right, what about E2? Right, so here's going to be uy and vy, right? Now, existence of f prime. How do we interpret existence of f prime z? Now you calculate this one, and then you're clocking backward by how much of the angle? That was so that's the magnitude and the direction part. There is this, if you look at the formula of this one, there is this factor of e to the I alpha minus beta, right? Anybody remember what this beta is coming from? Beta is this angle of this one, angle of that one compared to that. That's the beta. Okay? That's where that one is coming from. E1 is already horizontal, so E1 cases beta is 0. Right? If vector is that, and when you calculate the derivative, because of the complex number being in there, there's just, you calculate that directional derivative. Final step in f prime of z, slightly different from UV picture, is one more step is clocking backward by this beta angle, right? If you're clocking backward beta angle, it is supposed to be exactly the same thing. That's the existence, right? If you look at one part ux plus I times vx, and after you look at the second direction, we have a second directional derivative. After clocking backward, you have to come back to that one, right? So what is the angle in here, beta? 90 degree, right? It's 90 degree. So we're going to clock this one backward by 90 degree. So does anyone know what happened to the 90 degree if you're clocking backward the coordinates? If I give you 2, 3, if you clocking backward 90 degree, what happened? It's supposed to be 90 degrees, the dot product 0, right? It's either 3, 2, negative goes there, and negative goes there, right? So the dot product is 0. Okay? Think about 1, 0. If you're clocking it backward like that, it becomes 0, 1, clocking backward 1, 0, right? Where should the negative go? To the 0, right? To the bottom. So that is the correct answer. 2, 3, think about clocking it backward 90 degree. That has to go to right 3, negative 2 in the fourth quadrant. Make sense? Yeah. You can experiment it to get the right sign. So this one becomes, that one as you're clocking it backward, what does that become? Vy goes up there, right? And uy goes down there. And you got to have negative there. That's the clocking it backward. By just comparing just these two factors, two directional vectors. But this thing will dominate all the other because of the linearity by Jacobian thing. Does that make sense? But this one is supposed to be equal to what? After you clocking this backward, it should be exactly the same value. That's the meaning of f prime of z exists. No matter which direction you see, you have a different directional vector, but If you're clocking it backward, you come back to exactly the one you calculated with the one approach. Doesn't matter how you approach, it all gives you the same answer. So therefore, these two things should be the same, right? After you're clocking it backward, these two vectors must approach the same. What is this equation called? Cauchy-Riemann equation. Cauchy-Riemann equation. If f prime of z exists, it means you have this u and v coming out of this function. They satisfy this weird equation. Okay? That's the Cauchy-Riemann equation. So I'm going to write that down. ux vx, well, it's there. It's ux equals vy, vx equals negative ui. Right? That's Cauchy-Riemann equation. And you can verify this one with the, z squared and x squared and things like that. All right? So I'm going to ask you to verify some of this thing.